everyone, this is continuity part 3, and we're going to start with some questions for you to answer. The first question is looking at the function here. Do we have continuity at x equals 0? The answer is no. So if you're just using our old definition, when you get to 0, you would be lifting up your pen. Sorry, this is a fail right here. Okay. You're lifting up your pen at 0. You also have a discontinuity at 0. It's a removable discontinuity at 0. For all of those reasons, there's not continuity at 0. Part B, does the limit as x goes to 0 of f of x exist? So do we have a two-sided limit at x equals 0? Answer is yes. As we approach 0 from the left and as we approach 0 from the right, we're going towards the same y value. Next question, is f of 0 defined? The answer is yes. Remember, that means, is there an output at x equals 0? And there is an output at x equals 0. It happens to be down here where the closed circle is, but there is an output, so f of 0 is defined. And the last question, does the limit as x goes to 0 of f of x equal f of 0? And that answer is no. So the limit as x goes to 0, that is some positive y value, like whatever this number is up here, whatever that y value is, that's the limit. F of 0 is asking about the y value or output at x equals 0, and that's some negative number, whatever that y value is, which is a negative number, the output is negative. So we know the limit is some positive number, the output is some negative number, so they are not equal to each other. And this is what causes the function to not be continuous at 0. So the reason the function is not continuous at 0 is because although we do have a limit, sorry, my stylus is being weird. Although we do have a limit, it's not equal to the output at 0, and that's why we don't have continuity. So this is the formal definition of continuity right here, and we're talking about continuity at some value of some x value. So it could be any x value, and they just happen to call it c. So you have to have all three things in order to have continuity at c. So there has to be a limit as x goes to c. And if you're struggling with that c, just imagine that as some number. And we'll show you some examples in a second. So there has to be a limit at that place. There also has to be an output at that place. And finally, the limit has to equal the output, and that would create continuity. So all three of those things have to be happening. If we go back to this example, the first part is, do you have a limit? Yes, we do. The second part is, do you have an output? Yes, we do. The third part is, are they equal to each other? If they were equal to each other, then we would have had continuity because it would have looked like this. But that's not what we had. So the third part of the definition, after you've established you have that limit, you have an output, the last part is, are they equal to each other? And so all three of those things have to be true in order to have continuity. There's a limit, there's an output, and they're equal to each other. So this last part of the video is formatted like the worksheet that you're going to do to give you practice with this format. If we were in class, I would be having you write out all this notation on whiteboards. We'd be checking it. We'd be really working on that notation. And it's a little bit more difficult to do that remotely. So I'm not going to push that right now, but hopefully in the fall, we'll get to see each other and work on that together. So in order to make it easier for you, I've basically just given you an item bank, 1, 2, 3, or 4, and you're going to just write a number for each question. So I'm going to do this top row to show you how this works, and then you'll try the bottom row, and then you'll be all set for how the worksheet is formatted as well. So the first option is there is continuity because the limit equals the output. The second one, there's not continuity because the limit doesn't exist. The next option, there's not continuity because there's not an output. The last one, there's not continuity because although we have a limit and we have an output, they're not equal to each other. So the only thing that's a little bit weird here is this marked value of C. So I'm going to try to help you with that. It says at the marked value of C. So you're going to determine, do you have continuity? Yes or no? And if you don't, what's the reason why that you don't? So if we look at part A, the marked value of C is talking about the number that they wrote in. So they want you to examine the continuity at x equals 3. And so what that means is that your x value, your C value is 3. And so if it helps you, I mean, you probably won't do this every time, but the C value is 3. So if that's helpful for you to see, that's what that means. So first, do you have continuity at 3? That's the first question. And no, we don't, because we're lifting our pencil there. We can see that there's a jump discontinuity at x equals 3. So then we're just looking at what the reason is. And you start with the first one. So number 1 says it is continuous, so we're not choosing that one. But then we go to the next one. Is it because there's not a two-sided limit? And you always start with that first part of the definition. So if I'm looking at this, it's like the yellow is the first thing I check. Then if I have the yellow, I would go on to the second one. If I had the second one, I would go on to the third one. So we're going to go in order. Do we have a two-sided limit as x goes to 3? And we don't. So I'm going to write 2 is my answer because I'm saying we don't have continuity because the two-sided limit at that value doesn't exist. The reason I know that is because when I go towards 3 from the left and when I go towards 3 from the right, I'm not approaching the same y value. So that two-sided limit doesn't exist. So the continuity definition is falling apart at the very first part of the definition. The first part of the definition says, do you have a two-sided limit at that number? No, we don't. So we don't have continuity because we don't have a two-sided limit. Okay, next one. Letter B. So now our value of C is 1. So C is 1. And if you need to visualize that, all the C's are 1s. Okay, so for this one, do we have continuity at x equals 1? No, we don't. We have a hole in the graph at x equals 1. So we're not going to choose this one. Number 1 says it is continuous. Number 2 says it's not continuous because the limit does not exist. So we actually do have a limit here. As you approach from the left and from the right, we do have a two-sided limit. It does exist because from the left and the right, we're approaching the same y value. So we do have a limit. So we're good on part 1 of the definition, or this one. The next one says it's not continuous because f of 1 doesn't exist. And that is true. So I'm going to put a 3. There's not an output at x equals 1. So because there's not an output at x equals 1, we can't have continuity. And so if I'm looking at this definition, everything's falling apart at number 2. The first part says there's a two-sided limit, which there is, and the second part says you have an output at that number. We don't have an output at that number. So I'm going to choose 3 on this one because 3 says f of x is not continuous at the marked value of C because f of C doesn't exist. In other words, there's not an output there. So that's why we don't have continuity. Okay, next one, let's look at letter C. So letter C, our marked value is 0, so we're looking at 0. And let's use the definition this time. So let's go up here. Do we have a two-sided limit at 0? Yes, we do. As you approach from the left and the right, you're going towards the same y value, so there is a two-sided limit there. Number 2, do we have an output at that number? Yes, we do. The output is down here. Third thing, does the limit equal the output? No, it doesn't. The limit is a positive number and the output is some negative number. This is the example we already looked at. So for this one, we're going to choose number 4. Number 4 says we don't have continuity at the marked value of C because the two-sided limit doesn't equal the output. Remember, all these C's, you can imagine zeros there if you need to. But the big idea there is that, yes, we have a two-sided limit. Yes, we have an output, but they're not equal to each other. So that's what number 4 is saying. All right, and the last one, do we have continuity at our marked value, which is x equals 4? Yes, we do. That function is continuous at 4. You're not lifting up your pencil anywhere, and not at 4 either. So for this one, we're going to put number 1, which says we do have continuity at that number because we have a two-sided limit, we have an output, and those are equal to each other. The output is right here, the two-sided limit is there as well. We have continuity. Okay, and then there are some for you to try. So let me scroll out because I do like that definition showing at the top if I can. Okay, so you can use the definition if you like, but you're gonna ultimately try to end up with 1, 2, 3, or 4 for these answers, just like we did in the top row. For this graph I'm drawing on right now, it didn't have, I want you to look at x equals 1. There was no marked value, so I want you to look at x equals 1. Okay, so go ahead and take a look at E. What number would you put under E? So you should have a 2 here, because the first part of the definition is, do you have a two-sided limit? There's not a two-sided limit at 2, because as you approach from the left, you're going up forever. As you approach from the right, you're going down forever. So this one, we don't have continuity at 2, and it's because we do not have a two-sided limit. The very first part of the continuity definition is not held in this example. Okay, how about letter G? Letter G is going to be number 1. There is continuity at -2 because the two-sided limit and the output are the same. You can also visually see the continuity there, but when we get to calculus, we don't say it's continuous because I don't lift up my pen. You say it's continuous because the two-sided limit equals the output at -2. So that is number 1. How about the next one? Talking about this graph. That one is going to be number 4. So this one gets pretty far into the definition. The first part, do you have a two-sided limit at 1? Yes, you do. As x goes to 1 from the left and the right, you're approaching the same y value. The second part of the definition, do you have an output at 1? Yes, you do. You have a closed circle there, so there is an output. Third part of the definition, is the limit and the output equal to each other? And that is not true. So you have the limit up here, the output, the limit is like, what, around 4 or something, the output is 2. So that's going to be number 4. We don't have continuity at x equals 1 because although we have a limit and although we have an output, they're not equal to each other. So that would be the calculus reason you would give for this graph not being continuous at x equals 1. And the very last graph, go ahead and try that one. That is going to be number 3. So you're looking at our definition, the first part of the definition, do you have a two-sided limit at A? Yes, you do. As you approach A from the left and the right, you're going towards the same y value. Next part of the definition, do you have an output at A? X equals A. No, you don't. There's no closed circle. It's not defined anywhere. So this one is not continuous because there's not an output at x equals A, and so that is what number 3 is saying, that you don't have an output there. All right, great job. Hopefully that is going to help you with the worksheet because the formatting is exactly the same.